This is the introduction to your torque and second condition of equilibrium lab. I'm showing the first setup for part A experiment 1, and the first thing you want to do is grab 4 or 5 of these clamp weight hangers, and you're going to want to find their masses. So use the triple beam balance to find their masses, and use some tape and label them so that you know what their masses are thereafter. Also, on the triple beam balance, get the mass of your meter stick. Then first set it up as in experiment number 1 here. I have the pivot point, which is just one of those mass clamps flipped upside down. I have the pivot point at 30 centimeters. So without this added mass on the left side, due to all of the mass of the meter stick concentrated at the center of mass, it would want to rotate this way. In our perspective, a clockwise rotation. But at 10 centimeter mark, I have added a certain amount of mass and included the mass of the clamp, and I've gotten them to balance. That means the torque due to this force over this moment arm, this should be a 20 centimeter or 0.2 meter moment arm, the torque it creates in a counterclockwise fashion is equal to the torque that the center of mass creates at this point with its moment arm, 20 centimeters or 0.2 meters, torque going clockwise. If those two torques are equal, then if you just call mg, m sub sg, the force of the weight of the center of mass, you can solve for the mass of the meter stick and compare that to what you just measured. The second experiment involving the torque balance is shown here. We now have the pivot point at 50 centimeters, so that force and that torque due to the center of mass is ignored because it goes through the pivot point. I added a certain amount of mass as called for in the laboratory experiment at the 20 centimeter mark, and I recorded that value, and I made sure to remember that the mass, the clamp for the weight hanger also has mass, so I recorded that. And then I went and took the amount of mass I was told to add to this weight hanger, including the clamp mass, and then had to find at what point did I reach equilibrium. At what point along here would it reach this sort of equilibrium. Don't copy my numbers here. I'm not using the same amount of mass as called for, but the idea is the same. The torque created by this weight on the left is a counterclockwise torque. It's exactly equal to the torque created by this weight hanger on the right. Notice their moment arms, the distance from the line of action of the weight force to the pivot point, and from the pivot point to this line of action of the force, you need to measure these distances or know them quite accurately in meters.